My name is Benedikt Bünz. I'm a faculty here at NYU Courant, the computer science department, where I work on zero-knowledge proofs, and I'm also a co-founder of Espresso Systems, which provides infrastructure for rollups. So this talk is very much in the intersection of what I work on. And we've already seen this, so I'm going to go through the beginning very quickly. Blockchains don't scale today. They have these famous 15 transactions per second, and really the goal is, even with rollups, we just heard they can go up to 150, maybe 1500 transactions per second. Even that, we still need a bit more, and we really want to, ideally, I think, long term, we want to blow Visa out of the water. But yeah, it just means we have a long road ahead, but rollups are certainly a big stepping stone. And the way that they do that is, so if we look at, sort of the basic reason why do blockchains only do 15 transactions per second? Well, the reason is that essentially every single transaction will update this layer 1 blockchain and update this, what we call the world state, which means that every single person running an Ethereum node will have to process and execute these transactions. And essentially this level of replication, both on the data end and on the processing end, is what slows down kind of these blockchains, and is what sort of fundamentally limits them to these low transactions per second numbers. So the basic idea of a rollup is to batch many transactions into one, right? So the rollup itself, as we just heard, it's a blockchain on a blockchain. It has its own rollup state, which is akin to the world state. It basically then, in the world state, puts what we call a Merkle root. This is sort of a cryptographic summary or commitment of your own state onto the main chain. And then it gathers a bunch of transactions from a bunch of users and updates its rollup state, its local state, and basically pushes a summary of that onto the world state, including this transaction list. Yeah, we just saw all of that. So the key points here are that you can take hundreds of transactions of a rollup states and batch them into a single layer 1 transaction. And this essentially can give you up to 100x speed up. And so the rollup operation sort of, I just very briefly go through this. As a very simplified, we have this rollup sequencer, or sometimes called rollup operator, which... Yeah.
Just to clarify, it's like the way you frame it now is like that it's the commitment to the revised state that is being posted.
Mm-hmm.
But so, and then early, like in the last talk, it seemed like he was emphasizing the transactions. I guess part of this is the data versus like the actual roll-up smart contract, right?
You have both. You generally have a commitment.
Yeah.
But so commitment is cryptographic to the entire rollup state. However, a commitment itself, basically, so what is a commitment? Well, it forces the rollup operator to basically use one world state, and it cannot change its mind about what the world state is. However, you cannot, from a commitment is compressing, so it is 32 bytes, no matter how large the rollup state is. So just information theoretically, you cannot recover the rollup state from the commitment, right? It's just from 32 bytes, you cannot get to terabytes of state. That just doesn't work. There's a lot of magic, in cryptography, but that just doesn't work. So what we also include as just pure data, this data availability problem, is the list of all of the transactions. They can be even posted in some compressed form. Essentially, that is implicitly, what you might say is implicitly, this is also, you could recover the state from that. It's essentially just for efficiency. Like you don't really need, technically you don't need this commitment to the world state. It's just for efficiency. It just makes operation better to also have that.
But, so I'm also just trying to understand the mechanics of so part of what I'm getting at is that there's both sort of like the data posting we're talking about is like the blobs, right?
Mm-hmm.
And the other thing you're talking about is like a roll-up smart contract that is transitioning its state, and that's where this commitment is coming, right? Mm-hmm. So like there's sort of like two interactions that are having to happen, right?
And what we'll see is that the proof system will need to link those two.
Okay.
So it's very important that, of course, when I do an update, that basically it's that my update is with respect to basically both the Merkle tree, or the Merkle root, which contains the basically this cryptographic commitment to this world state, and all of the transactions. So if those things are not connected, then it's not clear what I'm doing. So those things definitely need to be connected. We'll see that. Okay, so again, like I have this simplified operation. So let's say I have a bunch of transactions here. Initially, sort of these rollups, or especially these ZK rollups, could only process very simple transactions like transfers of money. We'll talk about sort of smart contracts and more interesting transactions later. But let's say Alice to Bob wants to have sent to ETH, and there's a signature that authenticates that Alice actually meant to send these funds, and there's some other transactions here. And then what we'll do is we'll update basically the world state based on these transactions. So I think Bob has now 2 ETH more, and Alice has 2 ETH fewer. And then we've computed a new Merkle root, and that's what we post now to the blockchain, including here, this is what we just talked about, the transaction list, which is essentially the stripped down version of these transactions. So you remove all the information that isn't necessary anymore. For example, the signatures aren't really necessary anymore in order to recover the state. You can even take all of this data and literally run like a zip compression on it. And that's what rollups do, right? Like you can literally take this data and you run a zip compression on it, because afterwards, then someone can take it from the blockchain and decompress it. This is just for making sure that you have this data available.
So what happens when there are multiple sequencers and Alice sends double spins on one sequencer and the other one?
Yeah, I mean today they need to essentially reach consensus amongst each other. Essentially today almost all sequencers operate in a single sequencer mode, partially for that reason. But if essentially the way that it would work if you have multiple sequencers is either you rotate them, so each time period one of them is in charge, or they run some small consensus protocol between them. In order to determine, basically, to get internal ordering.
So you can't send 2 like conflicting blocks to the same block, layer 1?
I mean, you can do anything, but then we'll see where the proof system comes on to hopefully catch these types of situations. But yeah, in normal operation, this would not happen. No. Okay. So I want to talk a little bit about. So this is, I hope. Sort of we've seen from Josh's great talk, like we've seen sort of all of these things already. I hope they map well to this. But I want to talk a little bit about the role of this sequencer, sometimes also called operator or coordinator. So the sequencer, it has multiple tasks. So it orders the transactions, it executes them, and then so to derive the new state, and then it pushes updates to the L1, sometimes also called batch posting. And importantly, the sequencer is needed for, someone asked like how is a rollup different from Coinbase? Well, the sequencer is trusted for sort of the operation and for things to run, to actually progress, at least at a reasonable speed, at a fast speed, but they're not trusted for security. So even if they act maliciously, we want to put things in place that, even if they go bankrupt, even if the roll-up company goes bankrupt, we want to put things into place such that the system can continue to operate or at least recover from that state, right? This is the key difference from sort of a traditional Web 2 world or a traditional finance world to a roll-up world. And the key goal of a roll-up is, again, this idea that the transaction rate on the L2 is higher than on the L1. But it's not so simple, right? So how do we verify that the rollup is doing its job? So this is, what we just saw. So we saw one approach to this, which are these fault proofs, or these optimistic, these fault proofs, which is basically the sequencer or the coordinator claims that it did its job correctly, And then we engage into something that is very similar to a law process, a lawsuit. And it's I think the law school is next door. Sort of one thing always, someone always wonders, with every sort of judicial process is, wait, why doesn't it go faster? Well, you can wonder the same thing here, right? Why does it take 7 days? But these things are complicated, and there's actually pretty good reasons why they're complicated. We just discussed them. And essentially, you can think of these fall proofs as, sort of an ex post law process that if something goes wrong, we have sort of judicial recourse.
So if I'm on optimistic L2 and I have funds there, and I do something bad, whatever, and I breach to Ethereum, so can you explain what's happened with 7 days? So if someone...
This is the next slide. Okay, so say Alice wants to withdraw some funds from her rollup onto the L1, right? Or she wants to move them. Even if she wants to move them from one rollup to another rollup, usually today you go through the L1. So today So how does that happen, and how long does that take? Well, let's dive into it. Well, what needs to happen? Well, she needs to send her transactions to the rollup sequencer. That takes, the sequencer aggregates and executes these transactions. I took them from Optimism, these numbers, but they're roughly similar for all of these systems. So this takes like 1 or 2 seconds, and then the rollup sequencer has taken these transactions and executed them. Can even be faster sometimes. Okay, then the sequencer takes a bunch of these, transactions, or bundles of transactions, and batch posts them to L1. I think on Optimism today, this takes about 5 minutes. Okay. Why does it take 5 minutes? Why don't they, they could post them probably sooner. Why don't they post sooner? Well, there's 2 reasons. The main one is just financial. The more transactions I have, the cheaper, or actually this is really the main reason. The more transactions I have, the cheaper it is to post to the L1. And then also there might be congestion on the L1, there might be higher fees, so I'm waiting for a moment where it is particularly cheap. I can even, as I said, I can use compression to get data costs down even further. Yeah.
So you said they. Who is they in this context? Like, is it the sequencer that is doing the...
Yeah, it's the sequencer. It's the rollup.
Is it part of like the job of the sequencer, or is
yes.
it just in...
Okay, it's really, I'm using sequencer here as a very blanket term. It is the rollup operator. So sometimes the rollup operator is split into, multiple parts, but it's the rollup operator, the rollup company does this.
What I'm really asking is about from the protocol side, who has, is this a permissionless thing where in theory anybody, because anybody can be listening to the sequencer, right? And in principle...
I agree. Today it is more likely to be permissioned. It doesn't really need to be. Okay. It is more, well, why doesn't it need to be? To be honest, yes, everybody could post. It's not that exciting to post.
Permissionless thing is this is where the incentives usually come in. Because if you say I have a permissionless system where anybody can post, as opposed to saying this guy has to do it, then, and so that's what I'm kind of curious about. Is
so what we could do, so today generally these things are permission, and we just sort of rely on reputation and the rollup company to do it. You could make it permissionless, but as you perfectly pointed out, then we would need incentives in order for people to actually batch post. Maybe
on every rollup right now, the batch posting is permissioned. There's some interesting technical problems with making it permissionless. Come talk to me later. Also a fair bit about this. But the right way to think about it is the sequencer. So most everything the sequencer can do, the batcher can do. So it's kind of under one logical role.
Yeah.
It's permission, but there is some level of power that the user has to make the sequencer do stuff, right?
So this is, these are these sort of sometimes called escape hatches or inclusion list. This is if the sequencer tries to censor me, I can include additional transactions on the L1. We already talked about this. I'm not going to go into those details. It doesn't really matter here. Yeah.
Yeah, just point out the question. There are 5 minutes, right, is due to performance of the L1, and the 1 to 2 seconds, right, is basically performance of the the sequence, right? So
Yeah.
we have now an L1 which is much faster. This 5 minutes could drop significantly.
Yeah, we're going to talk about how to drop these things, but yes.
Oh.
Yeah, but here basically you need to invest in hardware to drop this, and here you need to invest into Ethereum to drop the, well, not just invest in Ethereum, but in Ethereum infrastructure. Okay, it turns out that 5 minutes is actually not quite it, right? You then need to wait until the Ethereum block is finalized. John said it's 18 minutes, I trust him more than I trust sort of my information, somewhere between 13 and 18 minutes, until the Ethereum block is finalized. What does finalization mean? It means that there won't be a fork on Ethereum. So sometimes, it's very rare, but it sometimes happens that there's a fork on Ethereum, and then you can be sure, okay, this transaction will not be forked out. So then we have consensus on essentially the ordering of all of the transactions. So I know what the transactions are, and this is the state where someone could execute these transactions and know sort of what has happened. So it's from that point it's deterministic. However, the problem is that the rollup sequencer posted. Let's say the rollup sequencer is malicious. And it posted, a transaction, it worked together with Alice, and it said Alice wanted to withdraw 100 ETH, but Alice didn't actually have 100 ETH, right? Alice only had 1 ETH. Well, the problem is, what happens then is we can't wait for that, right? We need to wait for our law process to settle, right? We need to wait for our judicial process to settle. And this is the famous 7 days that we just talked about. Yeah.
Okay, but so you're taking the case where the thing that the initial thing didn't actually happen, and you need to wait for it to kind of be overturned, right? But like the flip case where you're doing something and you see the state transition and you know it's valid, then you know the challenge is going to fail, right? If it's challenged. So like basically what I'm saying is in the flip case of like when I'm just doing something and I see the state transitions and I see that they're legitimate, why do I really care about the 7 days?
It's a very good question. So if I'm honest, and I think everybody's honest, why do I care about the 7 days? Well, the problem is,
so even if other people are dishonest, like they can't prove something.
Yeah, sure. So the thing is, I know that this transaction, like let's say I'm Alice, I know that my transaction was honest. Yeah. And even like someone, we talked about, I think John mentioned Coinbase, right? If I sent money to Coinbase, they can sort of immediately accept it because they can, execute everything and know that it's honest. Yeah. The problem is, who doesn't know that it's honest? Well, other smart contracts. A smart contract doesn't know, right? The smart contract, another smart contract on Ethereum, or another, like a smartphone operator, someone that runs an Ethereum client and just a smartphone. How do they know that it's honest? Well, in order to do that, they would have to execute everything. But the whole point was that not everybody has to execute everything, right? The whole point is to offload the computation. So I have to wait these 7 days, even if I'm honest, if I want to use these funds on another smart contract. So for example, if I want to even bridge them to another, to another system, to another rollup. So even though I personally know that I'm honest, and even though if I was honest and everybody's honest, I still need to wait for sort of the law to settle.
But the way you answer that, the significance of the 7 days isn't that the 7 days is the thing that makes sure that the outcome is correct. It's just the convention that has to pass before we take that state as essentially finalized. So let me use, because you're talking about the law, like the obvious analogy that comes to mind is some lawsuits are wrongly decided, right? And so by the same token, you could have an instance here where essentially something, there's a state transition that is clearly invalid, but for whatever reason nobody challenges it, and 7 days pass, right? And so, but your answer, it sounded like, was like, but at the end of the day, like let's say you're doing it, you're bridging from layer 2 to layer 1, the layer 1 smart contracts have to have a sense of what happened, and so there has to be kind of like a finality to that.
Right.
And so that's where the 7 days comes in, but like equally it could be a shorter period, and it's just the states end up like more frequently being wrong.
So the problem is that it's, before those 7 days are over, the state is in some sort of quantum state, right?
Yeah.
Where it could be valid or could not be valid,
My
right?
point is the usage of the 7 year is like, it's a convention. It's not like 7 days is perfect so that the court case.
No. It's a convention. It's a
You
convention.
could make it 3 days. It's just you would affect like how frequently.
Yeah, it's a risk trade-off.
Okay.
You know, and this exactly actually, I'll get to this point in the next slide, but it's a very good point, right? It's not an absence of a fraud proof.
Yeah.
Is not a proof of absence of fraud. Even a wrongly challenged, like let's say, like, you know, I have a fraud-proof game. I see a fraud-proof game, and the sequencer wins. Do I know then that it's not cheating? No, I don't. Right? I could, you know, it could have like, you know, won against someone. Like it could have won against itself. Right? It can play a fraud-proof game with itself, and then like make it look like it's winning. So these fraud proofs are, you know, they're not a perfect proof, which is why I have to, you know, have these weird conventions and choose some period of time where I think that it is reasonable for someone to, you know, execute this, play the game, and so on and so forth, right? Okay.
I have 2 questions.
Okay, we have time for one.
Yeah. Do we have any data about challenges and how soon they happen?
They almost never happen.
Okay. The second thing is that what happens if we discover it on the 8th day?
So, by the way, okay, how would this actually happen? Like, this will never happen. If it's discovered on the 8th day, after 7 days, it's settled law. We just take the state, whatever it is, even if it was wrong. This is exactly your point. Like, even if it was wrong, after 7 days, it is settled law, even if it was factually wrong. So if I'm withdrawing funds, you know, then I've been able to steal funds. By the way, so how does this actually happen? Does anybody know, like, how would this actually happen? It is, in my opinion, it is very unlikely that one of the big sequencers would actually act malicious. How would it happen? The answer is North Korea. North Korea would hack a sequencer. I mean, this is very real, right? So North Korea, very motivated to get, you know, sort of funds. And they've been hacking these protocols, and they've been hacking these single points of failure for years. And what they would do, and which is a very, very real risk profile, is that they would hack the single server, right? You know, and they're incredibly sophisticated. You know, I could talk for hours about sort of, you know, what they do in order to hack these things. They would hack them, and then they would, you know, sort of, yeah. So if that's really the risk profile, the risk profile is not, you know, optimism or arbitrum. I mean, unless you're very paranoid, it is likely not optimism and arbitrum going rogue. Maybe for the smaller rollups, it's a bigger risk. It is, you know, they're op security, right? It's like really what you're betting on is, you know, sort of their OPSEC guy or girl versus, you know, sort of a motivated nation state.
Can you explain it? So I have money on optimism.
Mm-hmm.
I do agree.
Mm-hmm.
After 13 minutes, I can right away deposit it in a Uniswap smart contract, or I need to wait 7 days?
You need to wait 7 days. Because the Uniswap smart contract has no idea whether the fraud proofs will succeed or not.
So this is like a kind of related question also how you were answering to Fahad before. So given that this information is still like observable, like what is preventing the smart contract still to be faster and being conditioned on like the proof being there at later date? So I might want to have a smart contract that is based on the information that is there already at the beginning, and then if it is turned out to be fraudulent, then
So
like
you
the
can,
condition on that as well. So what prevents it?
Nothing prevents it. People actually sort of, you know, the problem is you likely won't be able to send. I mean, nobody would code a roll-up smart contract that sends out real funds before the you know. It's like it's the same thing as, you know, in your wire transfer, right? There's kind of different periods. It might show up in your account beforehand on your UI, and you could certainly code that. But do you actually have the funds, or, you know, does it need to go through Fedwire and all of those things? It's kind of similar like that. And the way that we actually encode this, for example, what can happen, right, and what happens in real life, someone can give you a loan, right? Someone can say, and you know, someone can say like, look, I know this money is going to come. Here, I'm going to give you a payday loan, right? It's exactly the same mechanics as that, and we can encode all of these things. And you know, there's just sort of So a lot of, when sort of end users bridge, they oftentimes don't go through this process. They essentially go to a third party. They send them money on the rollup. The rollup sends them, that bridge sends them money on the L1, and sort of that can happen much, much faster. They just then take the risk, and when they want to rebalance, they need to go through the slow path. So, yes, you can totally code this up. Yeah.
What is the magic behind 7? Why not 5?
There's no magic. So it's just a risk reward. It's just a risk trade-off. Okay. Last question, and then I'm going to continue.
So, if we already have the social consensus on 7 days, then do we really need blockchain here? Why don't we just have a database and everyone agrees on the final state after 7 days if there's no challenge?
Okay, so the problem with just have it, why can't I, can't the rollup sequencer just, say something? Well, the problem is that the sequencer, if it's malicious, it could tell you one thing. It could tell me a second thing, and it could tell Aviv a third thing, right? It can, tell everybody something different. And how do we know that we're all hearing the same thing? That is what a blockchain does, right? It's consensus understanding. Okay, so this talk I want to talk, a bit about how we get rid of these 7 days. But even if we get rid of these 7 days, there's still these 5 minutes and 13 minutes. Once we get rid of that problem, there's still a lot of other problems. These 5 minutes and 13 minutes, even that is not very, I thought we're building the financial system of the future, right? I don't want to, if you tell a Gen Z person, you have to wait 20 minutes for anything, they won't do that, right? And so how do we, get rid of these things? Here we know, okay, we can throw hardware at it. That's actually a pretty solved problem. For this, you should go to Ben Fisher's talk later, who's my co-founder at Espresso System, and this is essentially exactly what we work on, is trying to reduce these time periods to also order of seconds. But yeah, we'll point forward to that. So again, we already talked about that. The absence of fraud proofs does not mean the absence of fraud. I think we had a great discussion of this. And yeah, we need to wait such a long time to basically allow people to do these fraud proofs, even under very, very adversarial conditions. So congestion, so-called DDoS attacks, and so on and so forth. Okay, so how can we solve this? And here I want to point to sort of the talk that I gave, I think, last year at the same forum on these proof systems. So we're going to use some crypto magic, and the crypto magic is called the so-called proof paradigm. So in general, we often have this in blockchains, where, and you can even imagine this in other systems, where you say you have one user that produces some data, let's say a block, a rollup operator, and then it broadcasts that data to, and this data may be particularly large, and it broadcasts that data to everybody in the system. Well, and then everybody has to process this data and check that it is correct, right? This is how blockchains, traditional L1 blockchains work today. And the idea of a proof paradigm is that instead of broadcasting the data directly, we pass it through this magical proof protocol, which produces essentially a certificate that asserts that the data or the block is correct. And this certificate can be short and very efficient to check, even if the data is large, right? This is the key property here. And then I can just broadcast the certificate, and then everybody just has to check that the certificate is correct. So more generally, we call these things proofs of program computations. So the idea is that sort of Alice says, so from a computer science point, we say that sort of Bob wants to have some, or we agree on some program P, on some input X, and Alice claims that the output of the program is Y. And then she can basically run this proof algorithm, which depends on the program P. We'll talk about that in a little bit. Basically, which produces this certificate. And then Bob can verify this proof using an efficient verify function, which also depends on the program P, and output 0, 1. Interestingly, these algorithms are entirely public. They don't require any hidden keys. Okay? So let's make this slightly more concrete. It's still mathematical. Suppose the program P is the program that computes the Fibonacci numbers. Right? Fibonacci numbers 1, 1, 2, 3, 5. You take the previous two numbers, add them, get the next one. It turns out that on n equals 50, we could have all done it in our head, but I'm just giving you the answer that this is 1, 2, 5, and so on. Okay, so what Alice can do is that she can basically, on input 50, she can produce the output, and then she produces this certificate, which basically says that, which shows that the 50th Fibonacci number is exactly this value. Well, how could you produce this certificate? Well, there's some trivia certificates. I could just give you the Fibonacci numbers 1 through 49, and you can just check between them. But that's not very efficient. So ideally, I want to produce a certificate where the certificate is independent of 50, independent of n, or only logarithmically dependent on n. And it turns out that I can do that. And what we call these things SNARKs, succinct non-interactive arguments of knowledge. And essentially the idea is that they have multiple properties. And the amazing property here that we rely on is that the proof is short and that the verification is fast. So even if my program takes 1 billion steps, the time to verify can be proportional to something like 30. Right? So it can be exponentially faster to verify the certificate, and the certificate can be much shorter. Like in practice, they can be less than like 200 bytes. That's like a tiny, tiny text file. And they can be shorter than much more efficient to verify. So they're also non-interactive. It just means that I can just produce the proof. They're what we call an argument of knowledge. That just means that if I don't know, if the program output is wrong, I cannot produce a valid proof. This is sort of the cryptographic guarantee that we get. And then there's this whole thing. These things are called ZK rollups, and there's this idea of zero knowledge, which means that the program can have some private information, and I learn nothing about this private information. So here's the big lie of ZK rollups in the system. They have absolutely nothing to do with zero knowledge. There's no private information, right? We just talked about all of these transactions being public. Like privacy is important, or we can use the zero knowledge property if we want private payments. ZK rollups don't use ZK. They're really like SNARK rollups or validity rollups. It just doesn't roll off the tongue the same way. That's why we call them ZK rollups. But if you take away one thing, is that ZK rollups have not that much to do with zero knowledge. That's just one thing. So really the property that is important is this S, this succinctness, which means that it's more efficient to verify. How much time do I have? Like 5 minutes, 2 minutes, 5 minutes? Okay, great. So how do we use these things, right? I said we want to build, we want to build a ZK rollup. Well, so the idea is that, I guess this is approach 2 now, is that instead of using fraud proofs, I'm going to use these SNARKs in order to prove that I've run the rollup correctly. I'm essentially going to encode the rollup as a program and then build a SNARK, build a certificate to create this, also I'm using many different names for the same thing, produce a validity proof that basically I've done the operation correctly. So instead of basically having this law process at the end, I'm at the beginning going to prove that I did my job correctly. Okay.
Why is the non-interactivity such an important property?
It's a very good question. The reason why non-interactivity is important is that interactivity means that the proof is between, let's say, you and me. The problem is I can do that to convince you that something is correct. The problem is, what about the other 7.9 billion people in the world, right? If you're convinced, that doesn't mean that it convinces anyone else, right? So non-interactive proofs, the property that we want from them is that they're so-called publicly verifiable, which means that everybody can verify that the proof is correct. The interactivity part of it is actually, it's a necessary condition to get public verifiability.
So for example, like a secure network connection is an interactive process. That's not what we want here.
No, we need basically that the prover can, otherwise it's not a certificate, right? It's, it's a conversation. Sometimes the way that these proofs are constructed is essentially that I can take a conversation and I write down the transcript of that conversation, and that transcript essentially it acts as a certificate. But really what I need is the certificate that I can attach to the rollup block that says this rollup block was valid. Okay? And this is exactly how the sequencer works. So let's draw this up. So now what has changed, everything is sort of similar before, but now I've added this beautiful green box, which says it's snark proof of that essentially all of the transactions are valid. And the rollup smart contract also needs to change, in that now it needs to take in, all of the data and everything, but it also needs to basically only accept the new root. So in optimistic rollups, basically the rollup smart contract will accept any update. It just then we use the judicial process to resolve conflicts. In a validity rollup, the rollup contract will only accept these updates if the proof is valid. Okay, so it will run the proof verifier and check that it's valid. And the succinct proof proves that basically a batch of these 100 transactions are valid. And so why is it important that it's succinct? Well, it's important because I need to encode the verify function in this rollup smart contract. And that needs to be efficient, right? That needs to be significantly more efficient than rerunning all the 100 transactions. Otherwise, I should have just run the 100 transactions, okay? So it's cheap to verify the proof even on a slow L1 proof. Yeah. Well, 1 minute? Okay. Okay. Yeah. Okay. This is. I think I can end in 2 slides. Perfect. So what is exactly this statement that I'm proving? Well, I'm proving basically given the old state root, the new state root, and the transaction list. This is what we talked about in the beginning, right? I need to include all of these things. I need to connect them through the proof. I need to prove that basically, each of these accounts, like the details don't really matter, but basically I'm proving that all the signatures are valid and all the state updates have been done correctly. I'm really basically what I'm doing is I'm taking this program, I'm encoding the rollup operation as a program, and then I'm basically proving that it was run correctly. So what has changed? So this was sort of the role of the sequencer before. It would sequence, it would execute, and push transactions. So now we added a step, which is this proving step. So now the sequencer also needs to prove the correct execution of the transactions. So if we now finally look at sort of what the speed of rollups is, or sort of I guess I should have called this the speed of the ZK rollup. Well, what we got rid of, is what we added something here, which is that we need to aggregate and execute and prove all of the transactions. So we've actually made this slower. This is now a few minutes. There's a lot of work being done on making this faster, and there's a tremendous amount of progress being done. I think someone, Succinct Labs, recently posted that they can prove Ethereum blocks, or 90% of Ethereum blocks in 12 seconds. So there's a lot of progress being done here, but part of this progress is also just throwing hardware at it, right? Like this is what we're very good at in computer science, is just throw more hardware at it, and we can do that here. So why? Well, now we've made it worse. We added a few minutes here, but the important thing is we got rid of this, right? We totally got rid of this fraud-proof period. It's not needed anymore. The second the block is posted on Ethereum, you can sort of immediately transfer your funds away, and there's no more ambiguity here. Okay, so the end result is that sort of the rollup contract on the L1 ensures that the coordinators or the sequences cannot cheat, and sort of I say anyone can act as a coordinator and approver. This is not true in reality. This is my sort of my academic hat. I think if you wear a systems hat, this is actually quite complicated. But at least in theory, this is true. And nowadays, sort of we put even more power. Like they need to be, they need to have a lot of GPUs in order to run these proof systems efficiently. Okay. Thank you very much.